Good afternoon, folks. Thank you very much for having me here. My name is, my real name is Shigeo, Ohshima, but locally nicknamed as Jack. It's easy to remember, so just call me Jack. Currently serving as the technology executive for the SSD and also covering memory. So both technology, I'm responsible for that. So today, I'd like to present with the new 3D flash memory. We call it BICS. That's trademark of Toshiba. BICS Compatible BICS. With this new flash memory technology introduced to the SSD and storage application, what can we do in addition to the 2D? And in conclusion, I would like to summarize with the Toshiba SSD solution to support the storage applications. So let me start from the very high level Toshiba corporate vision. We basically have two big business segments to focus. One is the something we call energy associated. In other words, it's a heavy industry oriented. But today we focus on the second one, which is the largest focus in terms of innovation, and we spend the biggest money onto it. That is storage. And starting from the chip and drive level, with the hard drive, SSD, and non-component flash memories, we contribute to all of the data storage application, namely data center, server, and storage array. And very high-level storage market trend up to 2025, and this is very often recently referred to that very common number. These numbers, zettabyte. Currently, the around 2013, 14, 15 timeframe wise, the data created all around the world was 4.4 zettabyte. That includes not only the data to the store and data not very, the structure. So those data, 44.4 zettabyte, may include the data such as the paper, like a brochure, and also the whiteboard writing. So this is not necessarily always need to be stored, but the data really need to be stored. We call it demand storage. Wow. We can support from many storage media. It's around 1.5 zettabyte. And according to many white paper investigation by analysts and also internally investigated by Toshiba, data explosion in 10 years will happen. Just a 10x increase in terms of created data down to 2025. And in comparison, the storage devices we can create in many ways, tapes, DVD, Blu-ray, or car, or SSD, whatever. Overall storage demand is somewhere around 6.6 zettabytes. And looking into the two major players to the other storage devices, one is the flash memory, the other is the hard drive. This is a combination of internal investigation plus external analyst white paper. But for the flash memory, three major market segments. One is the retail, cars, and also the smartphone. And the biggest growing is the SSD for sure. And after 2020, and the growth of this SSD segment is the largest, and going up to 3.7 zettabyte in our estimate, and which also includes we take the portion of this hard drive. So the hard drive overall zettabyte, exabyte volume will be decreased drastically in these 5 years. So overall, by 2025, together with the flash-based and hard drive-based storage to support this created data will be around 4 zettabyte. So So out of 64, 66, we can support, the Toshiba will support 4.1 zettabyte overall. I know it's not enough, but in order to support some more, every flash vendors, not only Toshiba but other suppliers in the world, have to build at least 10 more fabs in the world. That's not very easy, and a huge investment will be needed. And taking a look at the, especially the enterprise-based memory and storage hierarchy, basically there are 3 different tiers. Tier 0, 1, 2, depending on how hot the data may be. How hot means how often you write and read the data. Today, it's relatively simple. There's a CPU here, and below there's a high-speed DRAM. And tier 1 warm data arena, we have 2 devices, rotation device, high-end, mid-end, and SSD. And tier 2 cold data, there's a nearline hard drive, much larger density with the compromising performance. And down below, there's a tape and optical devices. And by 2020, people all predict that the things are becoming more complicated, and lots of variation will be existing in between in these tierings. Namely, down below the CPU, there'll still be DRAM for sure, but together with DRAM, non-volatile memory, hopefully together with our R&D research, the magnetic memory, internal access will become a rise. And in the tier 1 warm data arena, together with the mission critical hard drive, we define, thanks to the additional technology in the name of a 3D flash, we can expand the opportunity of a 3-path SSD to the high-end direction, namely performance-oriented, and also the low-end direction, penetrating into the cold data occupied by nearline hard drive right now. These are 2 additional areas, thanks to the 3D technology, we can expand the opportunity of a flash-based storage. And needless to say, the biggest portion is the capacity-based SSD, which have already outnumbered in terms of capacity the mission-critical hard drive density. And latency-wise, I just calculated from the latency access time to the distance. Just calculating with the speed of lights. So easier to understand is that the data in the processor, L1, L2, L3 included, it's within the 3 meters. And the DRAM data is somewhere around 10 to 30 meters. So takes some time, but it's still close. And down below, the server storage, SSD, 2 types of PCI, high speed, and also the currently more available SAS and SATA storage. It's far from the CPU. It's around 30 kilometers to 300 kilometers. Not very, close to get the data from there, but the density-wise, it's much larger. And also think about the hard drive and nearline. Those hard drive guys, it's far from us. It's more than 2,000 miles. So I think it's corresponding to San Francisco to Hawaii, far away. So not frequently visit, but the data is huge. So what we have to do from now on, together with the flash memory application or more, is that getting this data much closer to yourself and keep the density and as much as possible and make the access latency much faster. And also, the gap between these 2 memory devices, flash storage devices, DRAM and SSD or flash memory, is becoming unfortunately high. We call it storage gap. Fortunately, because of the continuing high-speed implementation of DRAM versus the density-oriented flash memory innovation, staying at the basically the same performance. The gap is growing higher and higher, unfortunately. We have to fill the gap. And I don't have any time today to talk about this SCM storage plus memory, but like Intel first introduced last year, something we call storage plus memory, and Intel wording, they call it the crosspoint memory. And anyways, every flash memory and memory vendor is working on this new device, SCM, to fill the gap between DRAM and flash. And different explanation showing depending on the application and how you process the data. Compare with the current hierarchy versus the 4 or 5 years from now. Thanks to the newly introduced 3D flash, again, Toshiba's 3D flash is called Breakout stackable. And with this 3D flash, fortunately, this gives us a wider opportunity for flash to be extended in the high-end and low-end direction much widely. Namely, on top of the regular application arena, with the high-speed technology called TSV through silicon via, we can reach to the high-end to take care of the high-speed performance close to the in-memory computing, such as online transaction. On the other hand, down below, closer to the cold data arena, in the name of Hydropower storage, we can add 1 more bit per cell, so 4 bit per cell or QLC. This is the additional technology thanks to the 3D innovation. So with this high-end and low-end direction, we can expand the opportunity flash memory application much wider to correspond to many variation of applications. So let me briefly talk about the components. We call it big flash. So this is how we build it. It's very high level, almost a cartoon. But now we are facing the physical limit of two-dimensional floating rate based flash memory. This is we call the 1 unit, or a minimum unit of flash memory storage. We call it strings. This is a 2D XY horizontal shape structure. NAND flash memory strings. Here's the source right here to connect all of the strings to the source voltage. And the other side is connected to the each bit line in red. And the green one is a control gate or word line. So cross section of this yellow active layer in the silicon wafer, and this green wiring is a memory cell for each. Unfortunately, this structure is now seeing a physical limit for the further bit scaling. So what we are going to do is everybody stand up to the vertical direction, or stand up, then line them up, then connect. That's how we make it for the from this 2D to 3D. Basically, the structure remains the same, but because of the vertical structure, the memory cell type is changing from the cross-sectional to the cylinder, so that each active layer, yellow, is kind of a pipe, and the cylinder. And cross-section of the word line in green and the yellow pipe is the 1 memory cell to be stored. So increase the density dramatically because XY direction, there's no change. Only the Z direction we explore. We can increase the density of memory cell by stacking them in 3 dimensions, X, Y, and Z. So even though we have one more dimension Z direction, it doesn't necessarily mean that we don't have to scale anymore X, Y direction. We have to do to increase the density for more. So this is how we are planning to build the future generation of 3D. Not just adding the number of layers, it is essential, but that's not everything. we always have to think about the memory cell size scale. So this is the cross section of each memory cell. Like I said, this is the cylinder. And surrounded by the green guide, this is a word line or control gate. This is each memory bit. And we have to keep scaling to make a better cost-effective solution per chip. But for every vendor, this is a very, very important innovation or optimization to make the best cost-effective memory. Z and X, Y combined together to make the best optimization for cost per bit. And here's our overall roadmap for the 3D PICs. Starting from generation 2 last year, and we are now in production of Gen 3. And next year, followed by the Gen 4 for more number of stack. Currently, last year we started with the 48 layer stacking, and this year we've been successful to achieve the 64 layers, and possibly very close to 100 3-digit. We'll be able to reach to the more number of stack with the Gen 4 technology. And keep in mind that this black circle means simply the completion of a development and the beginning of the production. So, like I said, 3D flash memory gives us more opportunity to extend the application in the storage hierarchy. So, starting from the top end direction and followed by the bottom end direction. First, high performance to reach to the memory gap. So, this is what we have already explained at the Flash Memory Summit back in August. The high performance with the low power and high density all coexist with the additional technology in the back end, packaging technology. We call it TSV, that's a through silicon via. Last year, first time at the Flash Memory Summit, I introduced for the first time the TSV-based, technology-based flash memory with the A19 technology. Now we have achieved the 3D flash memory together with TSV, reaching to the very high speed, clear data I up to 1 Gbps. And we have a solid plan to continue this roadmap for the more number of density and more number of the flash interface and more number of die stack. So currently, the first time introduced with this over TSV with the 3D flash PICs, which enable the higher data rate, higher than 1 Gbps, even with the 16 die per package, and very high density thanks to the bond wireless. Through silicon via technology, we could diet some die sizes, enabling double density. And also, together with the high efficiency, low power circuit design, TSV can achieve a very, very low power consumption, down to 45% power reduction. And here's the proof of concept. Actually, this is the real hardware data management. So there's a competition, how far you can go. Unfortunately, the bond wire-based conventional technology packaging technology base, it will be end up at somewhere in around 740 Mbps. You are not able to see the data I anymore. Whereas, thanks to this TSV technology, without any additional parasitic bond wire capacitance or inductance or resistance, you can see very clear data I even up to 1.2 Gbps. So this is one good example how TSV technology together with flash can achieve high-speed interface operation with the very high density. And we talk about the power next. I'm sorry. This is a real picture of currently available, TSV technology together with 3D flash PICs. We have already achieved 32 die cross section. But usually in one package, flash memory has some limitation in terms of the number of chip stack up to 16. 16 is even very difficult. You lose some yield and interface and performance-wise, there's lots of limits to make them operate at the highest frequency, both from the data I and also the power. But technically, TSV technology could achieve up to 32 die stack without sacrificing power or performance. And here's a very brief summary of how TSV can be differentiated. Like I said, the smaller and more cost-efficient die size enables the double density of a chip and the double density of package. So enabling 32 die stack with the a little bit smaller die size for each, you can achieve the double density with this TSV technology-based flash. This is density advantage. And also performance, needless to say, thanks to the lower capacitive load for each I/O pin, you can achieve even at the SSD level almost the 3x of performance improvement. This is one case for the SAS application at the limited power throttling at the 11 watts. And at the limited power specification, you can achieve up to 3x performance for the, in this case, random IOPS. And power dissipation, at the same performance, like sequential write vector per second, eventually you can achieve up to 45% power reduction. So, long story short, you can make a choice. At the same watt, same power, you can achieve a higher performance. At the same performance, you can achieve a much lower power dissipation. So you have a flexibility for choice. And here's another direction, the lower end direction, expansion with the 3D flash. That's 1 more bit per cell addition. As you know, floating gate technology, 2-dimensional, already reached to the physical limit, simply because of the number of electrons per cell can be stored. Just assuming this is a relative number, assuming our latest and maybe the last floating gate technology with the 15 nano die, assuming there's 1 electron can be stored in a 4 bit per cell MLC, TLC case 3 bit per cell, it's only half electron can be stored. So in different explanation, you see a 50% or a read error, unfortunately. On the other hand, thanks to the 3D dimension, realization of X and Y enable more electrons can be stored in one cell. So even the same MLC specification, you can store more electrons, almost 6 times. And that means you can achieve much better TLC, 3D per cell operation, thanks to more electron per cell. And that also means some expected idea. You can add 1 more bit, keeping the enough electron per cell. In our desk calculation, this enables 1.5 electron per cell. So this is a good room for the chip to work as a QLC. And the new update is this is not just a simulation. This is a real hardware data. We have already achieved a good VTS distribution of a QLC. 16 separated independent level can be achieved per cell already. So we are now reaching very close to the real production stage. And good advantage of QLC SSD, no question about performance compared with the hard drive, no problem. And power-wise, at the same active power specification, Hydropower, of course, it's almost nothing. And workload-wise, this is the one disadvantage of flash because of the limited endurance of each cycle. However, thanks to the bigger density, the workload for each drive can be pretty much friendly. So not too heavy for the workload for the QLC SSD. So QLC totally has advantage in high capacity and high performance and low power at the relatively relaxed level of workload. And here's a direct comparison of how you can replace hard drive with the QLC SSD. Number of devices, no question, we have a much higher density than hard drive. Currently, near my hard drive, somewhere around 8 terabyte to 10 terabyte in the real production. Whereas with QLC SSD can achieve more than 100 terabyte per drive. So very, very dense. And of course, no question about idle power. Idle power for SSD flash is almost zero. Whereas idle power hard drive, they still need to keep rotating, eat some heat. So no question about the heat, the power. And overall, footprint-wise, only one device is needed versus they need 12 devices. So real estate-wise, it is also an advantage. And overall SSD technology, putting all technology together as a Toshiba's SSD solution, finally. So why Toshiba? Simple. Flash memory, we invented. So we know everything about flash. And we are still the number 2 huge memory flash supplier in the world. And stable supply with our own fab. And also the very quick deployment of a new generation flash technology. And also quick new technology adoption to storage, namely SSD. Own development, develop flash memory and optimize control design in-house. And also covering every market need. We call it swing lanes. All the swing lanes can be covered by Toshiba in-house. So this is also a very good choice for the customer to select why Toshiba. And this is already announced in July and July. The 64-layer Generation 3 Gig Flash press release has been already made. And also back in July 15, new memory fab. This is purely for 3D flash. New fab fabrication line 2 was completed and we started huge production already. So chip is ready to support all of the storages, QLC, TSV, and mainstream flash, whatever. We are ready to produce. We are ready to produce some more. So all I need here is purchase order. And lineup in more detail. Like I said, we cover all of the swing lanes. Swing lane means 3 major interfaces: SATA, classical, SAS, high-end, and also newly introduced PCI and VX Express. We cover everything via both for enterprise and data center application and the PC-oriented client application. And of course, the bottom line, we also support all of the retail channel devices for sure. So swing lane coverage is also very important, and only the flash supplier can make it. And the final talk is about the additional, advantage of Toshiba as a semiconductor manufacturer. It's a package. So BGA-based single package SSD. This is what only I believe the semiconductor manufacturer can make or optimize. So 95% shrink from the commonly available 2.5 down to package BGA. And also the currently available NVM module, 82% diet to the package base. That's a very good advantage. And also the some additional feature. We have implemented the BGA package SSD without using DRAM. So there's some sacrifice, but we have a good memory control technology called HMP. So this is a very cost-effective way without using DRAM. And this is what we received at the Flash Memory Summit. Most innovative flash memory application BG series. This is what we received for the BGAs. And overall, this is the very high-end roadmap in the enterprise and data center support. We can cover all of the swing lane. And on top of that, we are now planning the very high-end ultra-speed PCI drive together with the newly introduced TSV. And finally, in closing, Toshiba can contribute to high performance and low power with the newly introduced TSB and one more bit for the cost-oriented application as well. And the smaller form factor semiconductor manufacturer's new solution, BG SSD. So all we can do for storage application with the flash-based we can support all of these segments. That's the talk I have to cover today, and thank you very much for your time. I appreciate it.